Okay, so in the last few videos we looked at Sylow theorems, proved them. There are 3 Sylow theorems. Remember that they describe Sylow p subgroups of a finite group G. The first one says there is always a Sylow p subgroup. The second one says any 2 Sylow p subgroups are conjugate, and the third one says the number of Sylow p subgroups must satisfy some conditions. So there is a range of possibilities. So in this video I am going to do some problems, and these problems will illustrate how to apply Sylow theorems. So the first thing that I want to do, let us call it a proposition. So I will show that any group of order 15 is cyclic. Okay. So this is a very strong statement. So remember, if you have a group of prime order, we already know it has to be cyclic, because you take any element that is not identity, its order must divide the prime number. So it must be all of the, it must be that prime number. So the subgroup generated by that element must be the whole group, but certainly that argument fails for a group which has non-prime order like 15. So how do we show that a group of order 15 is cyclic? So in other words, we are saying that there is an element of order 15, and that is not clear. All we know is that there is an element of order 5 and there is an element of order 3, but how do we know there is an element of order 5? So, and this is where Sylow theorems come into play. So we will show if G is a group of order 15 rather, then G is isomorphic to Z mod 3Z cross Z mod 5Z. Okay, so I do not remember whether I have talked about products carefully before. So quickly we describe product group. It is very simple. So Z mod 3Z cross Z mod 5Z. So remember, Z mod 3Z is a cyclic group of order 3, Z mod 5Z is a cyclic group of order 5. So we take elements a comma b, the first one in Z mod 3Z, the second one in Z mod 5Z, and we add them. So I am going to use additive notation here. So it does not matter what notation you use, but we do component wise. Okay, so in other words, a comma b plus c comma d simply is a comma c plus b comma d. Okay, and inverse of a comma b will be minus a comma minus b. Identity will be 0 comma 0. So Z mod 3Z cross Z mod 5Z is a group under this. So I am going to say that any group of order 15, this symbol stands for isomorphism, is isomorphic to this. Remember that there is always a group of any given order, namely a cyclic group of that order. So this statement applies to that cyclic group also. So every group is isomorphic to this, hence to the cyclic group. So now let us work with an arbitrary group. Let G be a group of order 15. So let us look at how 15 decomposes as a prime number, prime factorization. So it is 3 times 5. So G has at least one Sylow 3 subgroups and Sylow 5 subgroups, right. Let us say S3 is the number of, I am going to use small s3, number of Sylow 3 subgroups, and S5 is the number of Sylow 5 subgroups. So now the third Sylow theorem says what? third Sylow theorem says S3 divides 5 and S3 is 1 plus 3a, right. This forces S3 to be 1. Remember, if S3 divides 5, it must be either 1 or 5, but 5 does not have this property. So, S3 is 1. Similarly, S5 divides 3 and S5 is 1 plus 5a. Remember, a is some integer, of course, that is why 5 cannot be written as 1 plus 3a. This forces S5 to be 1 also, because only numbers that divide 3 are 1 and 3, 3 is not of this form. So, in other words, G, remember the whole point is that we know nothing about G, other than that it has order 15, but using only that we say G has exactly one Sylow 3 subgroup and G has exactly, so let us call this H, and G has exactly one Sylow 5 subgroup K. So, it has exactly one Sylow 3 subgroup and exactly one Sylow 5 subgroup. And now by second Sylow theorem, H and K are normal in remember, again I want to stress this again and again, we know nothing about G, that is the whole point. We can conclude this for any group of order 15. Of course, we know G is order 15, but nothing more. So, because there is only one Sylow 3 subgroup, any two Sylow 3 subgroups are conjugate, H must be normal in G, similarly K must be normal in G. So, note that H is a Sylow 3 subgroup. This implies H has order 3, but that means H is isomorphic to Z mod 3Z. Okay, this is a consequence of first isomorphism theorem way back. If you have a group, cyclic group of certain order, first of all H is a prime order group, so it must be cyclic, and any cyclic group of order 3 must be isomorphic to Z mod 3Z. Similarly, K is isomorphic to Z mod 3Z, Z mod 5Z. Now we claim, consider the map from H cross K to G. So, what is this map? I send a, so this is the Cartesian product H comma K, it goes to H times K. So, H and K are elements of capital H and capital K, right, but capital K and capital H are subgroups of G. So, small h and small k are elements of capital G. So, I can multiply them. So, I claim that this is an isomorphism. And remember, this proves that any group, arbitrary group of order 15 is isomorphic to Z mod 3Z cross Z mod 5Z. So, to prove that phi is a isomorphism, we need to show several things. First, phi is a homomorphism. So, before that, we first show I want to show that H intersection K is E. Why is this? This is easy, because H intersection K is a subgroup of K, of H or K. It is a subgroup of H. By Lagrange's theorem, order of H intersection K divides order of H, which is 3. Okay. So, in other words, order of H intersection K is 1 or order of H intersection K is 3. If it is 1, H intersection K must be identity, because identity is certainly in H and K. So, it is in the intersection, but if it is 3, then H intersection K is okay, but then we also use that now, so assume this, okay. We also know H intersection K is a subgroup of K, okay. So order of H intersection K divides order of K, which is 5. So this can't happen, right. So this cannot be 3 because 3 divides 5. So order of H intersection K is a number that divides 5 and 3, so it has to be 1. Okay, this is going to be useful to us. H intersection K is just the identity element. Now let us show one by one that it is a first homomorphism, then it is 1 1 and then it is on 2. Why is it a homomorphism? What do we need to check here? To check, what do we need to check something is a homomorphism? We need to check that phi of H1 K1 times H2 K2, we want to check this is equal to phi of H1 K1 times phi of H2 K2, right. So we want to check that in order for something to be a homomorphism, you multiply in the left hand side group, apply the map, or you apply the map and then multiply, you get the same answer. Multiply first, apply phi, or apply phi first and then multiply. So what is this? Remember, the product is component wise. And this is H1 K1, phi of H1 K1 is that, phi of H2 K2 is H2 K2, this is H1 H2 K1 K2, this is H1 K1 H2 K2. So now the question is, are these equal? So now you must remember that I am not necessarily assuming that G is abelian. If G is abelian, of course it will follow immediately that these are equal, but I am not assuming that. However, I claim that we have, if H is in H, K is in K, then they commute. I claim that they commute. Why is this? Let us write two elements as follows. So we have H K H inverse times K inverse is equal to H K H inverse K inverse. So I am not doing anything here, I am just grouping them differently in a group that gives you the same answer. So H K H inverse K inverse, H K H inverse K inverse. But now remember that this is in K. Why is that? Because K is normal in G. Small k is an element of capital K, right, and small h is in H, but that is irrelevant, it is in capital G. So H K H inverse will be in K. So here is where you know both first, second and third Sylow theorems are being used. To show that K is the only Sylow phi subgroup, we needed Sylow third theorem, and to know that it is normal, we needed second Sylow theorem. So this is in K, of course this is also in K, so this whole thing is in K. But now let us look at this. This, because H is normal, that is in H, right, because H is normal, H inverse is in H, K is in G, so this is in H, this is in H, the product is in H. But we have already argued that K intersection H is empty, just the identity element. This means this element is the identity element, but that means Hk is Kh, because you can multiply by first K and then by H. So while it is true that G is not necessarily abelian, elements of H and elements of K commute with each other. Now let us come back here. We have H1 H2 K1 K2. This can be written as H1, interchange these two, which gets this. Okay, so phi is a homomorphism. If you can interchange H2 and K1, you are done. So this shows that Phi is a homomorphism. Phi is a homomorphism. We are claiming that it is an isomorphism. So, let us prove that phi is 1 1. So, suppose that phi of H1 K1, sorry, phi of HK, so you can do this, phi of H2 K2. But what is this? This implies, so if two things map to the same thing, I want to conclude those two things are equal. So, this is H1 K1 is equal to H2 K2, that is the map phi. It takes H1 K1 to H1 times K1, but that means H2 inverse H1 is K2 K1 inverse, but this is in H, this is in K. Again use the fact that H and K have nothing in common. This implies that if this element seems to be in both H and K, so this is E. This means similarly K2 K1 inverse is E. This implies H1 is H2, this implies K1 is K2. Okay. So, phi is 1 1. Now, why is phi is onto? Why is phi onto? Remember again what is phi? It is a map from H cross K to G, which sends HK to H times K. Okay. So, what we have shown is I claim that H cross K has 15 elements. So, suppose for the moment you grant me this claim, if it has 15 elements, it is a 1 1 map to G, which is also 15 elements, it must be bijective, right, it must be onto. In fact, we claim two why does it follow that it has 15 elements? It will follow, this follows. So, this implies first of all phi is onto, right, because phi is 1 1 and G has also 15 elements. So, the claim completes the argument that phi is an isomorphism. You have a 15 element set mapping to a 15 element set, but it is 1 1. So, it must be onto also. So, this proves the proposition, the claim that phi is an isomorphism. So, why does H cross K have 15 elements? So, first we show that, we can show that H cross K is a subgroup. Okay. So, I will leave this as an exercise for you. The proof is exactly as before, using the same idea that if you have H1 Hk is equal to Kh, you can use that. Okay. So, it is an easy exercise. So, this is easy for you. Then I claim that H cross order of H cross K, not claim, this follows, this is Lagrange's theorem, this divides 15. Lagrange's theorem says that it divides 15, but certainly order of H cross K is greater than 5, because K has already 5 elements and you are multiplying by H and these are different elements. So, it must be at least 5. So, the only number that divides 15 and bigger than 5 is 15. So, that shows that H cross K is 15, has 15 elements, and hence H cross K is, thus phi from H cross K to G is an isomorphism. Right. So, it is an isomorphism. Now, we have, so we showed that, we recall that H is isomorphic to Z mod 3Z and K is isomorphic to Z mod 5Z. So, G is isomorphic to Z mod 3Z. Isomorphisms are preserved by composition. So, G is isomorphic to Z mod 3Z cross Z mod 5Z for any group of order 15. So, in particular Z mod 15Z, which is a group of order 15, is isomorphic to Z mod 3Z cross Z mod 5Z, and which is further isomorphic to any group of order G. So, any group being isomorphism is a transitive relation. So, G is isomorphic to Z mod 15Z, and hence G is cyclic. This proves the proposition. We showed that any group of order 15 is cyclic. Hence, this is a very good application of the Sylow theorems. We have no way of proving that an arbitrary 15 order group is cyclic. I mean, how do we do that? There could be lots of groups, we do not know the structure of those groups, but the strength and power of the Sylow theorems is that we can conclude that any group of order 15 is cyclic. Now, let me as further examples of Sylow theorems, let me look at some problems. Show that any group, a group of order 100 has a normal subgroup of order 25. Okay. So, this is an easy application of the Sylow theorems again. So, we recall that, I mean, we know that order of G is 100, which is 5 squared times 4. So, if you want to look at, first of all, there is, so a Sylow 5 subgroup of G has order what? Has order 5 squared, because 5 squared is the largest power of 5 appearing in 100. So, we know that by the first Sylow theorem, we know that there is a subgroup of order 5, but why is there a normal subgroup of order 5? By first Sylow theorem, we know that G has a subgroup of order 25, but why normal? Why should there be a normal subgroup of order 25? And for use to prove that, we have to use the remaining two Sylow theorems. Let us say S25 is the number of Sylow 5 subgroups. So, I am using S25 because to emphasize the fact that Sylow 5 subgroups have order 25. So, by Sylow third theorem, by Sylow 3, S25 divides 4 and S25 is 1 plus 5a. Remember that the prime plays a role here, 5 is the prime that is relevant here. So, S25 divides 4 and S25 is 1 plus 5a, but S25 dividing 4 can be 1 or 2 or 4. 1 of course is a possibility, but if it is 2, it is not of this form, right? It is not, when you divide by 5, the remainder is not 1. Similarly, it can't be 4. So, S25 has to be 1. So, there is only one Sylow 5 subgroup, and by Sylow 2 it must be normal, right. So, that solves the problem. Just as an aside, let us look at Sylow 2 subgroups. 2 is the other prime dividing 100, have order 4, right. 100 is 4 times 25. So, 100 is 4 times 25. So, Sylow 2 subgroups have order 4. So, let us say S4 is the number of Sylow 2 subgroups. So, S4 divides 25 and S4 is 1 plus 2a. Okay, now what are the possibilities? If it divides 4, it's 1, sorry, it divides 25, it's either 1 or 5 or 25. Now 1 is certainly a possibility, but even 5 is a possibility or 25 is a possibility. So without knowing further about the group, we can't restrict choices anymore. So the number of SILO 2 subgroups is either 1 or 5 or 25. So we don't know which one actually happens. So this tells you both the strength and the limitation of SILO theorems. In the case of SILO 5 subgroups here, we are able to conclude 1 is the only option and it must be normal. But for SILO 2 subgroups, there are 3 possibilities, and SILO theorems themselves do not tell us how to eliminate any of those possibilities. Let me do one more problem along the same lines. Okay, let us say P and Q are distinct primes. Let P and Q be primes and suppose that P is strictly less than Q. Let G be a group of order PQ. Show that G has a normal subgroup of order. Okay, so I'll solve it very quickly. The proof is very simple, solution is very simple and similar to the previous problem. What is the idea? We want to show that there is exactly one SILO Q subgroup. So SILO Q subgroup of G have order Q. It's not Q squared or Q cubed and so on, right? Because Q is the largest power of Q appearing in order of G. So they have Q, SILO Q subgroups have order Q, and as always we denote SQ to be the number of SILO Q subgroups we know that SQ divides, so SQ is that SQ divides P and SQ is 1 plus AQ, right. But let us see, if SQ divides P, SQ must be 1 or P, but can it be 1? Of course it can be 1, but can it be P? Can P be written as 1 plus AQ? It cannot be, because P is smaller than Q. So P is smaller than Q means P can't be written as 1 plus AQ, because 1 plus AQ is more than Q. So G has only one SILO Q subgroup, right. We are using the third SILO theorem here. G has only one SILO Q subgroup, let us say H, and SILO 2 implies H is normal in G, because any two SILO Q subgroups are conjugate. So if you take H and conjugate it, it is another SILO Q subgroup, because it is a subgroup and it has Q elements, but because there is only one SILO Q subgroup, that must be H. So all conjugates of H are H, so H is normal in G. So this is the solution. Okay, so these two problems gave you some idea of how to apply these SILO theorems and why they are very powerful. Okay, so I will stop this video here. In one more video I will do some more examples and problems which illustrate how to use SILO theorems. Thank you.